A couple of weeks ago, I was on the trip with the Arctic Circle train. And even before, as a climate scientist, I was aware how fascinating but fragile our world is. But seeing certain natural phenomena up close and personal made me wish to understand the facts about our world and try to explain and share what I learned about them using everyday language. In the first episode, I was talking about the origin of aurora borealis and how to make night photography featuring northern lights. Today, I will talk about not so photogenic feature of our world, but a feature that presents a great threat for our own existence as we know it here on Earth. I will talk about permafrost and its degradation due to climate change. Almost 2 years ago, I have co-authored a project under the title SODEEP, which is a catchy abbreviation for Study of the Development of Extreme Events over Permafrost Areas. And just recently, European Commission recognized the importance of fostering our progress in understanding processes related to permafrost degradation and decided that the project is very well worth funding. In the aftermath of submitting that project, talking to my friends about what am I going to do, I have realized that not so many of them actually have any idea what is permafrost, and even less they knew about the very possible and disconcerting risk related to permafrost degradation. Actually, I myself until recently did not know much more about permafrost either, except very broad secondary school definition, saying that permafrost is permanently frozen ground for at least 2 consecutive years. Little did I know before joining the Terrestrial Hydrology group at the Max Planck Institute for Meteorology. Then I encountered people talking about strange landscape features such as ice wedge polygons and Thermokarst lakes. It took quite some time before I can see some of these landscape features indicative of permafrost from close proximity, and that was just recently when I embarked on the Arctic Circle train journey. Hello and welcome to my channel. I'm Dr. Goran Georgievski, a climate scientist, currently visiting at Max Planck Institute for Meteorology, but affiliated with Helcondcentrum Geest Haag, Institute of Coastal Research, and Alfred Wegener Institute, Helcom Center for Polar and Marine Research. But please, have in mind that I do not represent any of those institutions. Opinions expressed here are my own, and from now on I prefer to be known as Netizen Geo. Therefore, let me properly introduce myself. My name is Netizen Geo, and everything around me is permafrost. Even those bumps behind me are not giant molehills, but Thermokarst mounds caused by permafrost, near the Abisko Scientific Research Station. What is this guy talking about, you might ask yourself. What are these Thermokarst mounds? What is permafrost? Following text can be found on the info table next to the mounds. Quote, Thermokarst mounds caused by permafrost. The bog contains permafrost, permanent ground frost. This causes Thermokarst mounds to form, ice-filled peat mounds. Thermokarst mounds can be several meters high, but the Thermokarst mounds here are low Thermokarst plateau. Winter in Abisko usually only brings a thin snow cover. On the mountain marshland, strong winds normally blow the snow away. Therefore, the permafrost can extend deep into the peat, more than 6 meters, as measured here by the Abisko Scientific Research Station in 1984. Global warming is having a huge impact on the Arctic and the mountain permafrost. End of quote. Global warming, permafrost, Thermokarst, ice-filled peat mounds. Do you understand what I talk about? Well, couple of words not so often used in everyday language, some of them even not so long ago introduced into English language. Indeed, according to an article in the Annual Review of Earth and Planetary Sciences, the term permafrost is mentioned for the first time after the Second World War to draw the attention of American policy makers to construction problems in the American Nordland. If you're confused by the word Thermokarst but familiar with the word karst, these are quite similar geological terms. Karst is characterized by the caves and land surface depressions due to the dissolving of limestone by underground drainage, while ice melting below the surface in Permafrost region is the cause of Thermokarst landscape formations. Here are some more bewildering words usually heard in the Permafrost research. For example, Polygon-patterned ground, pingo, palsa. And I don't know how much polygon pattern you can see on the landscape photography here, but here is my best attempt to illustrate picturesque features that can be seen in the area underlined with permafrost. On top of it, it's the active layer, that is seasonally thawed soil layer between surface and permafrost. Patterned ground in the shape of polygons, 5 to 30 meters in plant diameter, is formed due to rapid cooling, resulting with permafrost thermal contraction cracking on an annual basis. Vertical cracks open due to contraction are filled either with the ice in humid condition or soil in the dry condition. The process was repeated perennially, produced wedge-shaped forms oriented vertically with apices downward. The wedges usually range from a few millimeters to 6 meters wide and are 4 to 6 meters high. Secondary school geography definition mentioned before is still valid, don't worry. But saying that permafrost is frozen ground for the period longer than 2 consecutive years is limited definition, only on thermic properties of the permafrost, temperature below 0 degrees Celsius, and gives only lower age limit for the ground to be frozen, 2 or more years. Nevertheless, there are many other features important for the frozen soil, such as ground material, biogeochemical and physical properties. Permafrost could consist of rock, sediment or soil, and can contain varying quantities of ice, which in turn results with varying salinity. Furthermore, soil and biotic cover and processes, as well as the age and the time of the formation, i.e., during the last glacial cycle that could be anything up to 100,000 years ago. All of these contribute to the wide range of seasonal thaw depths, resulting with varying permafrost stable position and active layer depth, which in extreme cases can reach deep down to 1,700 meters below the surface. All of these properties result in wide variety of surface landscape morphology types. And still, many questions remain to be answered about genesis, distribution, environmental control, and even terminology is confusing to non-geologists. Depending on the size and the mechanism of formation, the mound can be called pingo or palsa. Both of these terms are borrowed from Arctic indigenous people, the former from Inuit while the latter from Sami language. However, the following 3 slides attempt to illustrate simplified mechanism behind formation and evolution of permafrost landform. From slightly elevated, i.e. thicker active layer, underlined with an ice core and permafrost, and via mound, be it a pingo or palsa depending on the size, to collapsed pingo/palsa or Thermokarst lake. Here is what happens. Below the slightly elevated and thicker active layer in the moor or bog area, such as here in Abisko, where the winter freezing front penetrates relatively faster than surrounding areas due to relatively thin snow cover. Remember what they wrote on info table? Quote, "Winter in Abisko usually only brings a thin snow cover. On the mountain marshlands, strong winds normally blow the snow away." End of quote. So, an excess moisture from the active layer might be drawn to form an ice core inside permafrost. Furthermore, if the summer happens to be cold enough, ice core may persist until next winter and further grow during summer by drawing up surrounding water. This, in turn, contributes to the elevation of active layer, making the ice core better isolated in summer due to thicker active layer and allowing greater winter cooling, since the elevated surface tends also to have a thinner snow cover. This process is an example of self-enhancing positive feedback mechanism. After tens of years, Thermokarst mound can rise up to more than 10 meters high. However, after some hundreds of years, icelands may reach close to surface and growth mechanism is disturbed, since the active layer becomes too thin to support aggregation of ice. The ice melts instead, and surface layer collapses, eventually forming Thermokarst Lake. Just next to our newly born Thermokarst Lake is one older lake. The fact that Thermokarst lakes, in various stages of their evolution, occur next to each other shows that Thermokarst mound's collapse is not necessarily indicative of climate change. However, remember that this is just simplified cartoon description of mechanism behind permafrost landscape formation. In order to get accurate information what is happening below the ground, detailed measurements and their diligent interpretation are needed. Employing various techniques, including but not limited to coring, that is drilling and taking core samples from the ground, geophysical survey by means of resistivity tomography and electromagnetic mapping, as well as satellite observations. However, satellites cannot see permafrost since it is under Earth's surface. Therefore, expert knowledge and novel techniques of satellite imagery interpretation are needed, combined with the ground observation. These information are then used to understand processes related to the permafrost landscape formation and to develop theoretical models in order to predict future state of the permafrost. Nevertheless, these processes are still poorly understood and therefore either missing or misrepresented in the climate models. The following map from the international program concerned with monitoring permafrost parameters, GTN-P, that is short for Global Terrestrial Network for permafrost, shows in situ observation sites and distribution of permafrost. Permafrost classification recognizes continuous permafrost underlying 90 to 100% of the landscape, discontinuous permafrost 50 to 90%, and sporadic permafrost 0 to 50%. About 1/4 of the Earth's surface is underlined by permafrost, usually in mountainous and high northern latitudes, Arctic and subarctic regions. However, in the warming climate, permafrost is thawing, and as it thaws, the ice within the soil melts. This might present not only additional amount of liquid water that could contribute to the sea level rise, but also previously frozen soil carbon, that is organic matter, becomes available for microbial degradation, and the subarctic region becomes a new source of greenhouse gases instead of carbon sink, as it was before. Though it is fairly unknown how much of permafrost melted water could actually reach streams and rivers. This will probably present negligible amount in comparison to the other factors contributing to the sea level rise. Nonetheless, the impact of permafrost degradation on ecosystem might be incurable. Indeed, photosynthetic processes are large consumer of CO2, and subarctic boreal forest, also known as taiga, is one of the largest among them, and it was responsible for up to 60% of terrestrial sink for atmospheric carbon dioxide. However, there is a growing body of evidence that the net balance of ecosystem uptake of carbon dioxide in this region is weakening, and greenhouse gases emission, including both carbon dioxide and methane, due to increased microbial activity caused by prolonged warm period, summers are getting longer and winters shorter in active regions, and thickening of active layer depth, contribute to increase further warming. This is an example of positive climate feedback mechanism. With the global rise of the temperature, permafrost thaws, and previously frozen underground carbon becomes available for microbial decomposition, resulting with greenhouse gases emission, in particular carbon dioxide and methane, which both amplify effects of global warming. Estimates are that there is almost twice as much carbon captured in permafrost than in atmosphere. But please, Have in mind that all of our current estimates on potential sources of greenhouse gases involve considerable uncertainty, in particular because we do not know how thick is permafrost in certain areas. In addition to that, the methane is much more potent greenhouse gas than carbon dioxide, and how much warming in the next decades are we going to experience depends largely on the ratio between CO2 and methane that will be released in atmosphere due to the decomposition of carbon captured in permafrost. However, in the warming condition, plant photosynthetic activity rises. That means that plant productivity enhances atmospheric CO2 sinking into Arctic biosphere. And this is a favorite argument for ostrich approach and denial of the fact that the climate warming endangers our own existence on the planet. Unfortunately, amount of released carbon dioxide due to permafrost thawing seems to be much larger than CO2 sequestration in plants. No matter where you on the global warming controversy spectrum, the debate is political, and evidence indicates that warming is real. It is happening, and mostly due to increased anthropogenic greenhouse gas emission after the Industrial Revolution. Measurements indicate that Arctic has warmed 0.6 degrees Celsius per decade over the past 30 years. That is faster than any other region in the world, and almost twice as fast as the global average surface temperature. Furthermore, it looks like the boreal ecosystems that once used to be a carbon sink for atmospheric carbon dioxide has reached its turning point, in which it starts to emit the carbon dioxide and methane into atmosphere. Situation is not harmless, and I did not intend to scare you, but to inform you, and contribute to bridge the gap in science communication and to initiate two-way dialogue between citizens and scientists. It is fair to say that we do not know all what is to know, neither about climate change nor about permafrost degradation. However, what we know is quite worrisome and calls for common action. European policy-making institutions, such as European Commission, have recognized potential risks of climate change, adopting various strategies to address the impact of changing environmental conditions. And just as I'm preparing this video, the European Commission calls for a climate-neutral Europe by adopting strategic long-term vision for a prosperous, modern, competitive and climate-neutral economy by 2050. A clean planet for all. Furthermore, European Commission aim is to make 25% of EU budget climate related. Some of that money goes to the climate research as well. And project that I am working on is also funded by European taxpayers. In the course of the next 2 years, in the frame of the SODEEP project, we will bring together data from long-term in-situ observations and field studies as well as medium and high-resolution satellite-borne and aerial observations with state-of-the-art hierarchy of numerical models, both in global and regional climate simulations, as well as the Permafrost standalone model. All that with an objective to improve understanding permafrost-related processes that are largely ignored in today's climate models. Therefore, be aware, you'll hear me for sure talking more about permafrost, its impact on climate change and what we can do to reduce our carbon footprint. Paying taxes and investing in scientific research is not enough to mitigate the impact of climate change. We need not only to talk the talk, but also to walk the walk, and give our share and apply the best advices coming from scientific research into everyday life. Here are just a couple of things that immediately pops up in my mind that any of us can start doing right now in order to reduce climate warming. We should increase the number of meat-free meals in our diet and avoid meat from factory farming. As well, we should try to introduce insect protein-enriched food into our diet. Biking should be our favorite means of commuting, public transport or walking as well. And we should share our story and raise the awareness about the climate change. Indeed, it is somehow sad but true, or maybe just my imagination, a cognitive bias, but I believe that people are more influenced by the anecdotal evidence from everyday life and stories their friends tell than by an expert opinion. Therefore, I came as a friend, an expert, friendly expert, fellow netizen telling story what I saw on the far north, behind the Arctic Circle. The winter is not coming. So please, share my story and tell me yours, perhaps below in comments, about the changes you have seen in your environment, how these changes have affected you, and what are you doing to lessen the impact of climate change. Inspire the world, be a hero, be a heroine, and save the world. Let us know about things that you are doing and everyone can do to reduce climate warming. And one more thing you should know before I go. We shall never surrender. But climate scientists cannot save the world alone. Thanks for your contributions. Thanks for watching. Be inspired and stay curious. Cheers.